Hello everyone. In this video we are going to focus on volcanic hazards and we will also talk about monitoring and forecasting towards the end of this video as well. Alright, so let's begin with volcanic hazards. There are two main groups of volcanic hazards, the primary hazards and the secondary hazards. The primary hazards are the ones that are directly associated with volcanic eruptions, and they can include lava flow, pyroclastic flow, and the steams that are coming from the ground, some poisonous gas as well. For the secondary hazards are the ones or incidents or phenomena that occurred before, during, or even after the main eruption. Okay. And again, they can include lahar, landslide, or tsunami. Okay, tsunami can also be part of the secondary hazards of volcanoes, particularly when they are associated when we have a volcanoes that are submerged under the water, under the ocean. Okay. All right, these are the pictures for lava flow and pyroclastic flow, the ones that you already saw before. But I just want to remind you again that lava flow is the primary concern in shield volcanoes. So think about Hawaiian volcanoes, okay? Whereas pyroclastic flow is the one that has been the main concern in areas where we have stratovolcanoes, okay? Remember that these pyroclastic flow can go very fast, and this is very hot material, and they can be very, very dangerous, especially for those people who live near the volcano. All right, some stratovolcanoes, they can erupt and they can, violently explode, such as the one in Yellowstone, for example. And Yellowstone actually produced something that we call as caldera. And again, I just want to briefly remind you what caldera is. Caldera is a massive depression that form after a massive explosion or eruption of a volcano, such as like the one that happened here in Yellowstone. In Yellowstone, at least there were three main eruptions that occurred at about 640,000 million years ago. Sorry, 640,000 years ago, 1.2 million years ago, and 2 million years ago, as indicated by this map right here. Now, Yellowstone, fortunately, it is not as active as in the past, but it still shows some, hints of volcanic activity in the ground. So, for example, it still produces lots of geysers and hot springs, and these can also be part of the hazards associated with caldera. Um, so these are these are the geysers, and Old Faithful geyser on the left, Steamboat geyser on the right side, on the right of your monitor. And these are two of the most famous geysers that are there in Yellowstone. So what happened in these geysers or hot springs is that typically we have groundwater, and these groundwater coming into the system, okay? And because remember that we still have lots of heat here underground, so these water are heated up, and then they become less dense, and then that is the reason why when it becomes so low in density, it just shoots up and creates steams and hot springs that we see on the surface. To measure to measure how big the explosions associated with volcanoes, especially stratovolcanoes, we use a special index which is called volcanic explosivity index, okay, or VEI. Okay, VEI goes from 0 to 8, and volcanic eruptions are ranked according to four main elements. The first one is the volume of material ejected from the volcano, and geoscientists, they also measure the height of the cloud, produced by the volcanic eruptions, as well as the duration of eruptions. So eruptions can go for several hours, or they can go even days or even weeks, okay, or even years. Style of eruption is also another one that geoscientists consider to help rank the volcanic eruptions. So again, these are the four main elements that geoscientists measure to determine the volcanic explosivity index for an eruption. All right, this is the scale just to give you an illustration what VEI looks like. So typically VEI from 0 to 2, these can be considered as small volcanic eruptions, and everything above 4, this can be considered as large to very large volcanic eruptions. So for example, in the last video I showed the eruption of Mount St. Helens in 1980, right? So that eruption actually sit at about 4.5 in VI scale. And here, look at Yellowstone. Ooh, Yellowstone, look at this. Yellowstone release almost up to 1,000 cubic kilometer, and it actually sits at about 7 to 8 in VI index. And here I would like to talk about one of the one of the biggest volcanic eruptions in history, and that happened in Krakatau in Indonesia. Okay, so before the big eruption, it is called Mount Krakatau. Okay, but after the big eruptions, um, a small volcano develops, and that is what we call as Mount Anak Krakatau. And you will see later on why we changed why they changed the name of it. Okay, so Krakatau was located in an inhabited island, and it began erupting in May 1880. Okay, produces lots of excuse me, lots of volcanic material. Okay, let's start again. So it began erupting in May 1880, and it produces lots of a volcanic material that it could include ash, different types of rocks and steams and lots of explosions. But the main eruption, the biggest eruption, happened in August, on August 26 to 27, 1883, which is about 3 years after the initial eruptions. And these eruptions sits at about 6 in the VEI scale. Um, Many geoscientists believe that the seawater rapidly mixing with magma, this is the recipe for the big eruptions to occur in Krakatau, Indonesia. So some of the facts that are associated with with this big eruption is that the explosion heard almost 5,000 kilometers away from the volcano, and it produced one of the biggest tsunami that they ever recorded. Okay, that killed 36,000 people who live in the island nearby, and it produces lots of materials. Okay, it releases lots of materials, ash, pumice, steams, and many things. And these vast majority of volcanic materials, they can actually go into the atmosphere and cover the regions, and this caused the region over there to be in darkness in the next 24 hours after that main eruption in 1883. Okay, obviously the eruption was so big it destroyed the island. And this is also an interesting fact right here. The global temperatures fell by 1.2 degrees Celsius in the following year. So this is what the outline of Krakatau before it erupted Okay. So that is how big the island was, that stick out above the sea level. Remember that Krakatoa is a submarine volcano. Okay, so the base of the volcano is actually sits on the seafloor, and what we see on the surface is just the tip of it. Okay, so this is the outline of the volcanoes that sticks out above the sea level. And then what happened after that is that everything is gone after the 1883 eruption, creating this big caldera right here. So this is the new caldera of Krakatau. Nothing happening here in the middle. Not long after that, it turns out that there was one little volcano that developed after the massive eruptions, and after that this guy right here is called the Anak Krakatau. So what is Anak Krakatau? Anak Krakatau literally means the child of Krakatau. Okay, because this is a much smaller volcano that developed after the massive eruption of the main Krakatau volcano. All right, so that is the primary volcanic hazards. Now I would like to switch to secondary volcanic hazards. The first one here, the first example will be landslides. Landslide is a rapid downslope movement of material um, that can happen before the eruption, even before the eruptions, during the vibration before the eruption, or even during, as well as after eruptions. Okay. Maybe the best example for this would be Mount St. Helens, because Mount St. Helens initially, when it started to erupt, it actually produces a massive landslide that actually, so everything here on this side of the mountain or the volcano just collapse and goes down slope. And because of the collapse of this flank right here, it releases lots of pressure from underground, and it just goes violent. It just went violent after that. Okay, so that's how landslides can occur in volcanoes. Another example of secondary volcanic hazards would be poisonous gas, and they can be dangerous volcanic gases that can float in air, dissolve in water, um, and they can produce things like smog or acid rain or toxic soil, right? Especially, I would like to highlight a major incident that happened in 1986 in Lake Nyas in Cameroon, where they have volcanic activity on the surface, and it produces deadly carbon dioxide eruption that killed almost around 1700 people. It almost wiped out the entire village. That's what I heard. But it was very sad story, but this is something that we have to understand, that it could be something that is associated with volcanoes. And here is the picture of Lake Nyas, and this is the picture of animals um, that are killed by the carbon dioxide eruption. So carbon dioxide can be very, very deadly, especially when they occur in such high concentration as well. Okay. All right, so the last part of this lecture about volcano is something related to the monitoring and forecasting of volcanic eruption. All right, to monitor and forecast volcanic eruptions, we use a combination of these 6 different elements that you see here in this picture. Not this picture, this slide, okay? And that could include geologic history, seismic activities, the thermal and magnetic conditions. Geoscientists can also go out there and they measure the volcanic gas emission directly from the volcano. We can also measure the tilting and bulging, especially the swelling of the ground, in order to know whether there's ongoing activity or not. We also use some fancy tools such as remote sensing. So all of this, the combination of these elements help geoscientists to monitor and forecast future eruptions. So here's one example, for example. So here's the measurement of ground deformation. Okay, so here notice that we have a tilt meter here on the ground that measures the tilting of the slope of the volcano. So when there's a swelling happening, they can immediately know that there is an activity going on. Geoscientists can also go out there. For example, these two cool geologists right here, they go out there and they measure gas emissions that are coming out of the volcano directly. And I'm pretty sure this looks like a picture, another picture from Hawaii. And we can also measure, some thermal anomaly of a volcano using satellite images. So, for example, here is one of the volcanoes in Chile. Previously, it was thought to be dormant, but using satellite thermal monitoring, we can actually identify that there are two new crater lakes that are heating up on the volcano. Now, by doing all of that, a geoscientist can come up with a map, which is called hazard zonation map, that looks something like this, for example, right? This is the hazard zonation map from the big island of Hawaii. What happened here is that you can see the different shades of color right here. Now, based on the legend that we see here, it looks like the safest area in the big island of Hawaii is in the northern part of the island, because as you can see here, we have the shade of what, purple, maybe, right, light purple, which is right here in the lowest severity of hazards. And that being said, if you go towards the south of the island, you will encounter the darkest shade of blue right here, and that means that we are in areas with the highest severity of hazards. So in order to produce something like this, it requires a lot of work, geological mapping, dating, and correlation as well. And this is also another example of a zonation map, hazard zonation map in Mount Rainier in Washington. So what happened here is that they have measured, or they have mapped, the possible pathways for laharic flow to flow, basically. Okay, so, and everything here is typically associated with the main river. So by having this map, we can actually inform people who especially live in the vicinity of these rivers to be aware of the the lahar hazards, the potential threat from laharic flow from Mount Rainier. Okay, so I think that's it that I would like to talk about, and that concludes our topic on volcanoes, and I will see you again in the next video with other topics. Bye bye now.